Yeah, okay. Thank you, Felix. Yeah, as Felix said, that unfortunately, because of another arrangement, since I'm here nearby, so I'm heading to Heidelberg for colloquium. So I'm leaving pretty much right after the lecture. So if you have any further thoughts, further either questions or suggestions, then just simply drop me an email, then I will try to be in contact. And so obviously, I'm running short of time, so I think there are two reasons. One is that I think I went probably a little bit too slow than I should have for the first lecture, or two, it's the basic things I want to get everybody into the same pace, but I probably could have been a little bit faster. And the second reason is that towards the collider applications for today's lecture, I probably was a little bit too ambitious, put too much stuff anyway. So therefore, I won't be, for these two reasons, I won't be able to finish all the materials. However, the lecture notes will be, I think it's posted already, so maybe only 1 or 2 pages missing. So the lecture notes will be on, and that's complete. That's everything I want to say for this the school, and it will be there. And there will be missing pages I won't be able to discuss in class. However, feel free to read and to discuss and make comments with me. So today is the last lecture. I'm going to discuss the main features and what kind of basic knowledges, once again, you should know for the E+- collider and hadronic colliders for these two. So, but before we do that, let's summarize what we discussed last time. I told you that we should know something about basic detection. So that's what the last lecture. So in connection with the detector technology and also the observables for the particles. And it so turned out our standard model particles have such a wonderful structure, and we have the gauge interaction universality, all these properties there. However, in terms of observation, we need to know something. We need to know something realistic. Okay, so that's the kind of a summary to see how these particles may behave. So once again, these along this horizontal direction, it's almost like the layers of the modern collider detector setting. In the very, very inner set, it's maybe a millimeter size of the small chamber there. We call that vertexing. That's a silicon type of materials, and with the technology to have the best, so far the best spatial resolution. So far the best spatial resolution would be at order of 10 microns or so. So that's the order of magnitude. So therefore, the cross usually means doesn't do much, and check would mean that yes, that part will be connected with this particle. And second one would be the magnetic field. Then the band, charged particle is not neutral. And the third one is absorption for electromagnetic showers, basically electrons and photons. That's it. And the further one is very heavy elements, such as lead or other things, to absorb pretty much everything they can in the hadronic things, not only protons and pions and neutrons and neutral particles, neutral hadronic particles. Then you have energy absorption to heat up. No matter it's charged or not, you have this one spot at one particular location, then you know the angle. So you know that in that sense, you know the momentum too, the magnitude, pretty much all massless particles. Those everything here for the direct observation things are pretty much massless, as I mentioned to you. And finally, the muons will go further away to the chamber. Then this is the list. I'm not going to go over them one by one again, because we kind of discussed this already. It's largely based on the travel distance, which is based on the intrinsic lifetime, and then the decay length. I mentioned to you already that the decay length at 10 microns in that region is detector-wise resolvable or not. So therefore, translate this into pretty much speed of light, and translate into the time scale is about 10 to minus 12 seconds or so. So in that region, longer than that, it's kind of quasi-stable. Shorter than that, you don't see. It's immediately split into the decay products. So that's the thing we want to basically know. So electrons, for example, going through does not do any vertexing because it's stable, and it's absorbed. It's stopped. It stops at here electromagnetic. Tau, in contrast, is different. It's almost immediately decay. You have to reconstruct, but some of the fraction of that will resolve into a secondary vertex, because the lifetime is order for 10 to the minus 13-ish, 10 to minus 12-ish. So that's the lifetime thing. And then I will go through the tracking because of charged particle, and sometimes it results in the final state decay to electron, or possibly decay to muon, and maybe even hadronic, rho or pions, a few of them. So that's the behavior. You see, even electron and tau are both elementary leptons in our standard model with the universal interactions. Only difference is the mass. Now they behave very differently from the observational aspect. So that's the example. Then hadrons and so on and so forth, and I will not give the details. Finally, the heavy particles, that are those we are most interested in, not only for the reconstruction, but also for our future search. We are hoping to search for physics beyond standard model, and Higgs the last one. So this is the Higgs. Higgs largely decay to BB. Then all these the entries here refer to the decay products, and you try to reconstruct that. You reconstruct the Higgs. Of course, the Higgs decay, five decay channels have been observed. So just last month, this month, at the beginning of this month, is the ICHAP conference in Korea, and there was a lot of very nice update. And the BB bar channel was finally only recently confirmed up to 5 sigma level. So BB bar channel. ZZ channel was the early discovery. Gamma gamma was early discovery. Tau tau made it last year, 5 sigma, and so that's basically the decay channel. You reconstruct. So therefore, based on this knowledge, we hope to use this and to guide our thinking and for new physics search. Okay, so that's the point. So I stop here for the observational aspect. So for new physics search, once again, we have many ideas and to search for different things, but so far we haven't seen any, but we should not give up. We just don't know the scale. Physics is about any scale. If you reach the scale, boom, everything comes up. We don't reach the scale, we'll continue to work harder and explore deeper. So with many ideas, and we see that the Higgs to photon discovered already, Higgs tau tau, as I mentioned, all these are observed already. Then the Higgs ZZ is also observed. So that's the recent example that how the new particle discovery is being made. Then we have other new ideas, right? So maybe there are heavy Higgses, okay, in the extended Higgs sector in the supersymmetric theories, and there may be other partners like very similar to W and Z, but supersymmetric partners. We hope to we still have a valid theory there, but we haven't seen them yet. But maybe strongly interacting theory to understand the electric symmetry breaking sector to a deeper level, almost like a QCD type. You may have a new dynamics such as new hadrons such like technicolor, quarks, rho's, and so on and so forth. But whatever other new ideas you have, and we want to explore, and typically they eventually go out to the decay products to all W's, Z's, tops, and Higgses. And then WZ Higgs came back to the previous slide. That's basically the phenomenology idea. We are looking for new physics, but we are looking at their decay products, and the decay products would behave in such a way in our detector. So that's all I was thinking to say, and by the end of the last lecture. So that's the summary for the detection aspect. Let's move on to the colliders. Today, we are going to discuss both the colliders, E plus minus and hadron, and each of one of them has very distinctive features, extremely important, very complementary, and led us to this current level of understanding of nature. Okay, unfortunately, because of time, I probably would be more comfortable to have one more lecture, one more 1.5-hour lecture, but I don't think that's feasible. But I would cut the discussions short by half for each. But once again, the online lecture notes include everything I want to say, so they will be complete for your reading. So let's go to the lepton collider first. So Labrum Colliders have been extremely important for our understanding multiple Nobel Prizes and also multiple major discoveries. So let's start from a relatively recent and rather modern thing. It's called a Large Electron Positron Collider Lab at CERN. And in fact, there was a very large ring. By that time, it's pretty large. It's the largest ring there already. It's 27 kilometers circumference. And it is the LIC ring. LIC is using the same ring to just change the magnets and to run the proton version. Okay, so that is the original design to have the lab one to sit on the Z resonance. Therefore, the central mass energy, this is head-on collision. E plus minus head-on collision. Central mass energy is 45 on 45 give you around a Z pole, and you have the Z production. So luminosity by that time was pretty high, in 10 to the 31, which is somewhat higher than the linear collider. Linear collider was the Stanford linear collider here. So it's SLC, and running pretty much same time, but the luminosity is slightly lower because I will comment on this. The linear collider major challenge is about luminosity. It's very challenging to get a high luminosity, so that's why. Energy actually easier to do. You continue on, you will see that. But roughly speaking, the energy resolution 10⁻3. That's a benchmark number. Just remember, it's typical. The typical is the energy resolution is always 10⁻3 or so. I will come back to this point in great detail. So that's it. So basically, linear collider did have some polarization. In the future, it's even more important, the beam polarization. And this is 27 kilometers, and this is 3 kilometers at the slack. So that's Lab 2 is the same machine, but the increase the magnetic field. So basically, double the energy, increasing the magnetic field here too. And luminosity a little bit higher. The Lab 1 was able to accumulate about 10 million Z's, roughly in that range. So therefore, statistically, you immediately can take the root, 1 over root. So you will have the 10⁻³ accuracy for the electric physics. So roughly speaking, so this order of magnitude is important. You just quickly see how far you can go, so roughly. So it's about better than 10⁻³, depends on what kind of physics you're doing. So that's basically our level of the electric precision physics. Lab 1, of course, did not win the Nobel Prize. Lab 2 did not. That tells you an important message. Winning Nobel Prize is not measure, not the only measure for our science advancement. Okay, so the Lab 1, Lab 2 are extremely important, including the slack, for our understanding. So of nature, including in particular the electric theory. So absolutely necessary. If we knew, I think now I can say this, people may not agree. If we knew that this Lab 1, Lab 2 would not make a Higgs discovery, we still go ahead and do it. Because it's absolutely important for our advancement, for our high-energy physics understanding to a future level. We should still go ahead and do it. That's winning a prize is not the reason. That's not a reason, it's only a consequence. So that's the reason we want to emphasize that the E plus minus collider in the future is also equally important. So there are a lot of discussion for the future, and the International Linear Collider, we call the ILC, which is mentioned to you already, is up to a decision pretty soon, hopefully this year, with a real hope this year that will be a decision made. And the design was all done long time. The physics case was a lot laid out. I will give you 2 interesting, important physics cases for here. And so far, the site was chosen in Japan, northeast Japan in there already. So much higher luminosity and with a significant beam polarization also. And now the Higgs is discovered. The physics case is stronger. It's clear than ever. You have the target already. Higgs is discovered there already. So, and the Higgs production there is not direct production, E plus minus annihilation to Higgs because the coupling is too weak. That's the Higgs will have to couple to some heavy object first. That's because the property. Higgs property is to generate masses. Therefore, Higgs coupling to any particle is proportional to the mass. Okay, so that's why Higgs is so hard to discover. You have to produce some heavy particle first. Otherwise, Higgs will not come up. So you have to produce either top quark and shake off a Higgs, or produce a WZ and shake off a Higgs. So that's why the Higgs is so difficult. The Higgs comes last. You have to produce some heavy things first, and then the Higgs may come along if you are lucky. So then the International Linear Collider and so-called circular electron positron collider would try to aim at the Z Higgs pair production, and that is called Higgs factory. That's the leading Higgs production mechanism. It's not direct production, it's too small. You have to produce Z first, and then the Z will shake off the Higgs. So that's the one. I will come back to the example there. So then in the future, we may be able to do this at the click. I think that's CERN linear collider, which much longer. Linear collider, you can make this longer and longer. Just keep going. A circular collider, you fix your ring already, so you have to do a magnet. So linear collider, to make this longer and add a few more pieces. Now make the energy larger and larger. So that's the linear. So that's the current discussion for the machine. Now let's go to the physics then. I don't want to show the cross section yet, but I leave this here. Let's start with our notes. There are major advantages for the E plus minus collider as follows. So E plus minus collider has important features. The first point is that the E plus minus, the charge for the system is neutral. Okay, so you start from zero charge system. Okay, the system is E plus minus annihilate into some neutral system. Therefore, you can produce anything from a neutral state. You can produce pairs. You can use TT bar pairs. You can use new supersymmetric charginal pairs, and anything. You have this neutral. You have this neutral charge system. So therefore, it gives you the zero charge and also zero lepton numbers. So therefore, you can produce the barons. So it's no this conservation. So this one is very convenient to produce new things. Okay, so that's the first advantage. Okay, you can create new pairs. For example, like if you have a E plus minus annihilation into a photon or Z, then from here on, you produce new things. So it's no charge to keep up. There's no lepton number to keep up. You can produce anything, like even supersymmetric particles, charginos, new heavy leptons, and new heavy quarks, and so on and so forth. Any charge, even charge 2/3. So as long as you add up, so it's a very convenient thing to produce new things. As long as you go across the threshold. Remember, there's a threshold factor here. That is the threshold factor. We call it the velocity. You have to produce the particle on shell to propagate, to move. Otherwise, new particle. So that's the velocity. The velocity for this particle. If you go below the threshold, there's no particle produced, on shell particle produced. You cross the threshold. So that's the best thing. So therefore, obviously, it tells you already, you need higher center mass energy. So in order to cross any new threshold. So far, we haven't been able to reach the TT bar threshold yet. So therefore, TT bar has never been produced in the E plus minus conditions. But BB bar, of course. So and with, I even give you the B factory homework there already. Okay. So second thing is that we usually do a symmetric head-on collision on the beam on beam. So with this symmetric beam collision here, symmetric head-on. So therefore, the central mass frame is at rest. So the central mass frame is equivalent to your lab frame. There's no confusion. So it's the same frame. You sit in the lab at rest, and then the E plus minus system head-on collision will give that. Therefore, the kinematic is very well defined. So it's therefore give you the very good chance to do the good measurements. Okay, so kinematic is very clear, and the largest central mass energy available. You don't waste any kinetic energy. So you do as much kinetic energy you can produce from the machine, then all the kinetic energy will convert into central mass energy to produce any new states available or accessible. Okay, so that's the second thing. Now, with the well-behaved the beam properties, we understand the beam polarization and so on and so forth. The scattering kinematics well defined, the best defined. The best defined you can hope for. Outgoing two particles, its only thing is one polar angle. azimuth angle typically is not, but azimuth angle may be important towards the later point I want to comment on the polarization. Once you have the beam polarization, the azimuth angle is relevant. Otherwise, if you don't have the transverse beam polarization, there's no transverse preference. Therefore, the azimuthal angle phi is trivial. And only one variable is the polar angle, cosine theta, in particular for 2-to-2 process. Everything is so clean, so well defined. So that's you can perform precision measurements and so on and so forth. And because of E plus minus collision, it's really electromagnetic. There's no hadronic, no QCD strong interaction in the initial state. Final state, of course, you could produce charged particle and the color particle, and with the radiation, with the gluon, so on and so forth, they will come in. But that's in the final state part. Production part is purely electromagnetic. Therefore, the total cross section is not very large. And the good thing is that there's not very much background. So you produce something, you produce a threshold, it's standouts. It's not very messy. So therefore, let's say low background. Just have an estimate. If the some cross section I will show you there is sort of a picobarn, 10 picobarn, and because of that luminosity, I gave you 10 to the 34 luminosity at this. So this only gives you something like a sub-hertz. It's not even a hertz. The frequency, event rate frequency, is even not one event per second. So it's not very quick. So the cross-section typically is not very quick. Therefore, for this kind of setting, you even don't know this kind of a word like in Hadron Collider called triggering. Okay, triggering is that you have to select certain things to put them into on tape. But here you are able to tape any events as long as within your detector coverage. There's no major requirement for the selection. Tape them all. Cross-section not very large, not a huge number of events, in contrast to the Hadron Collider you will see. So it's daunting there, you will see. But that's a major advantage here. It's a lot of important things. And I said, finally, it could have a beam polarization. The initial beam, in particular for linear collider. In linear collider, you have a much better control. Circular collider, the polarization will gradually get lost somewhat. But the beam polarization is very important because of the electric theory is chiral. We know electric theory is not parity conserving. So you want to explore the new physics and electric theory. So, okay, so the beam polarization fits our physical the interaction scenario. Okay, so that's major advantage here. But you may not appreciate this, but you would appreciate this when I come to the Hadron Collider aspect to compare. Okay, so that's a major advantage. The major disadvantage. So the first one is about the synchrotron radiation. As we know, the synchrotron radiation has an energy loss due to the radiation. It's rather large. From your E and M, you know that if there's acceleration for charged particle and the acceleration for the particle will lead to radiation. But if you have the circular machine, that's called synchrotron radiation, and that is proportional to this the gamma factor, right, to the fourth power. So this gamma factor, the gamma factor is really the energy over E. Gamma factor is gamma is the energy over energy over mass. Okay, the momentum beta factor is a momentum factor. So we only gamma beta in our the simple special relativity parameters, right? Beta is the velocity, speed, and gamma is one. This is the gamma factor is larger than 1 to measure this gamma factor here. This the total energy over E is gamma factor's fourth power. But of course, as we know, this always depends on how large the curvature, how large the radius would be. More flat, is the less synchrotron radiation. So because of this, if you want to accelerate the electron and positron beam energies to order a few hundred GeV, and that can be estimated that the 100 GeV, you would make this very, very large, then much larger than the Lab 2 is pretty much reaching the limit to some extent. Yeah, Lab 2, this 200 GeV, yes, is almost it. Otherwise, you can make this bigger. The one I mentioned, the circular E plus minus, and then the radius. So far, the consideration for the radius for the circumference is 100 kilometers. It's huge. So it's still under discussion. It's not clear whether we will be able to do both. You have to choose a site. You have to have a big country like in China. So to host this, otherwise you run through in the U.S. you run through 5 to 6 different states. Good thing is you have 10 senators to support. Bad thing is that you have to negotiate. So it's just complicated. It's very difficult. So the circular collider to reach multi-hundred GeV would be very, very challenging, if not impossible. Okay, so that's one of the major constraints. Now, of course, you could try to make the linear. As I say, you make the linear, just keep adding up, and the radiation is much less. It's not the radiation is the same, different form, as we know. So, second thing is the difficulty is if you make this linear. That's a solution to significantly reduce the energy loss, energy waste. But then the focusing linear collider, the circular collider, you can circulate the electrons over and over 1,000 times. You increase luminosity by 1,000, 10,000 times. You have a 10,000 factor of 10,000. Linear collider, one shot, they're gone. They won't come back anymore. Then when you do that, there's 1/A factor, right? I told you the luminosity is 1/A. You make the A extremely small. Remember, luminosity proportional to how many particles you have in the first beam, how many particles you have in the second beam, bunches, and then how frequent you can collect them, and then how focused you can squeeze them into this. Then you have to squeeze this one, make this extremely tight so that you can increase luminosity, but that's very challenging. So then even from classical E&M, if you have two currents, they have interactions. Your two currents together, they repel, they attract, and so it's called beam straddle. It's even difficult to make this stable. So therefore, increasing the linear collider luminosity is the main challenge. In fact, that was experienced even at the SLC, the slack there already. So, but this will be extremely challenging. So that's the major disadvantage for this machine. So let's look at the physics aspect there. I'll start from physics. So typically, let's look at the 2-to-2 process. A simple, typical 2-to-2 process gives you this generic form. This is essentially 1/S behavior, threshold behavior. This threshold behavior typically refers to the final state of particle mass, right? You need to go across the particle threshold, and then this is E plus minus two particle A and B, and then dynamics. Whatever interaction dynamics you come in, this is only one phase space variable. Two-body we worked out in great detail. I went even very slowly, which could have been a little bit faster, but so that's what I went through. So this is only one variable. The phi is integrated out. Phi would not be integrated out if the beam had one transverse particular preference. The beam, so far we consider the beam has only longitudinal variable. Transverse polarization is non-existent for the moment. So therefore, this is a general formula, 2-to-2 process. You can always do. And beta factor in general, it is a 3-variable function. Particle A, final state, particle B, final state. That would be the one I gave you if particle A and particle B are equal mass. And this beta factor is given by this kinematic function. That is the most general form for the two outgoing for the velocities of the two outgoing particles, general form. It's derived in our kinematics. So this is the simple form. That's the general form. However, the dynamics may contain the real physics, Z production, W pair production, and T bar production, and so on and so forth. Let's look at this a little bit further, a few examples. Okay. So first of all, if we want to estimate the events, the observation, the events, as I mentioned to you, is convoluted with the luminosity multiplied by luminosity, but in fact convoluted by luminosity function. Luminosity is not always monochromatic, right? Even I said 10 to minus 3, the 10 to minus 3 spread. Okay, if you have a 100 GeV machine called Lab 1, 90 GeV, then 10 to minus 3 spread would be about a few hundred MeV. So a few hundred MeV, of course, in terms of the production, is seem to be small, but it may be relevant for certain particles. Okay, so let's think about that. Therefore, the events is really your cross section is equal to your cross section as a function for center mass energy squared. But this center mass energy squared is spread out according to your machine. It's not monochromatic. So let's use that as S hat. S hat is the real center mass energy for this E plus minus collision to take place. We sometimes more generally we call it the parton energy, partonic center mass energy, which means that the E plus minus beams are set up to come in with the machine design luminosity, the machine design the energy. But when these E plus minus really meet, they don't carry the same energy anymore. There's an energy spread because of radiation, because of other things. When they really meet, they meet at a slightly lower or according to your design. So that's the value we evaluate our production. That's real E plus minus energy to collide onto each other, calculate. But there's a luminosity spectrum for that. Delta function would be ideal, and then this, of course, S hat is equal to S, but there may be a spread. Typically, it's good approximation to parameterize this as a Gaussian. It's kind of a Gaussian distribution. So, and then 10 to minus 3 will be the Gaussian standard deviation around this energy. So therefore, you need to convolute this with this the beam and the luminosity profile. You need to convolute this with a luminosity profile. This luminosity profile is a function of your initial designed machine center mass energy that you hope to, but in reality it's changed a little bit. And then as a function of the ratio, tau here. And then you integrate over tau. This is the luminosity function here, and integrate over this one. And with normalization factor. So this normalization factor is how much luminosity you deliver. So the overall luminosity, this is supposed to be normalized to 1 in that case. You normalize to 1. Again, if this luminosity function were ideal, it's delta function. Then you simply integrate out this, you set this colliding energy to be the machine energy and simply multiply the accumulative luminosity. So that's where you usually estimate the event rate. Cross-section times luminosity, that's what we estimate the rate. But only under the case that you really have this ideal luminosity to hit at that particular energy value and to evaluate the cross-section at the value. So that's typically the case, okay? Such as that the luminosity function is typically some kind of energy spread, delta, and kind of a Gaussian type of thing. S hat S squared. So that's a Gaussian spread for a given design center mass energy squared. I should have a root like this form. And tau is the ratio, basically. Tau will be the 1. Tau will be 1 to hit on that. Let me give you two examples for this, two extreme examples for this situation. Now, suppose this energy resolution capital delta. Suppose your capital delta here is your energy spread. Your energy spread is called your delta. That is much less than some particle. Let's say this obviously, this argument here is only most relevant if you produce a narrow particle. If you produce a pair production spread out, and this convolution will not change cross-section too much because the function is very flat. So the function is very flat. However, if you have a resonance production, you produce a particle with a sharp shape, Bragg-Wigner shape, then you need to think about that. If the particle width is broader, significantly broader, which quite common is the case, okay, we have this in mind that for lab 1 at mz, the z width from your particle data book is 2.4 GeV. Z width is 2.41 GeV. So therefore, 10⁻³ energy resolution is a few hundred MeV, much smaller than this. Okay, so you really have a delta function delivery. So therefore, you have the delta function delivery, and what you do is that the physical resonance is narrow production. It's not narrow anymore. This is kind of a MZ with a GeV width, but your machine delivery is 100 MeV range. This machine. So therefore, you can tune your machine. You can tune your machine at 100 MeV here, 200 MeV there, 300 MeV there. You can scan. That's what they did. So that's how they measure the Z width in a model independent way. No matter what theory, who cares if it's a Z or something else? You find a resonance, measure the line shape. So they can scan the line shape of the Z, and they did. So of course, then from that they compare with this the theory contributions. It's agreed with the standard model, and agreed with standard model only if you count into 3 neutrinos. That's how the first neutrino counting actually comes from, rather accurate. If you put 4 neutrinos and the contribution to the width will be significantly shifted, that will not fit this line shape. That line shape measurement is model independent. Real measurement to see how wide this the shape, the Z shape is. So that is the only situation if you have such good machine, and you are lucky that the Z width, the physical width, is broader than that. So there was historically a different example. There was another example like this. In the other case, your energy spread, your capital delta, is larger than the physical width. Then you have a very different situation there. This actually took place a long time ago. Anyone remember some example along this line that really happened? Any example you can think of that the particle discovery, major discovery of the particle?
The J-psi.
Yeah, exactly. J-psi example. So of course, there's a following question that is beyond my lecture's scope. You should think, why J-psi is so narrow? There's physical reasons. Okay, so that's why it's a revolutionary. So J-psi was produced. Well, it's not understandable. So, but what this is? So it was a lot of theoretical discussions in and out. But in that case, the width is much narrower. The width for the J-psi is 3 point some. The mass is 3.18 or something. GeV for the J-psi mass. Let's say. The width so turn out to be order of 100 keV. Extremely narrow. J-psi particle is extremely narrow particle, even as much as strongly interacting. there are reasons for that. I hope you. And it's more on dynamics that I would not discuss. I promise not to discuss models, right? So there's a good reason for that. Of course, we understood later. We understood everything in and out, but that was the reason. Then your machine would never be able to deliver such a high accurate the beam profile. So therefore, it's extremely difficult to have this JSI. And your machine is so. Your machine, this is your machine. Your machine entity profile is like this. You hit or miss. You miss it, you miss it. If you're just slightly away from these particles, you don't find it. That's why it's so difficult. So you should go read the story, read the discovery story. It was really fascinating. So how they even found it. So you just move around. And then another thing is that if you are lucky to have your profile here, you encounter that, but the rate is still not very large. Only this part of luminosity is contributing to the production. The rest is not contributing. So only overlapping. This is the overlapping. Cross-section there, spectrum there. The integrated region is contributing part. It's the narrow width particle is very difficult to observe to find at the E plus minus. In contrast to hadron colliders is much better shape. I will comment on this later. That's why some people claim, which is not really completely true, but has a reason, is the hadronic machine usually is a discovery machine. You have a broader spectrum to pick up anything whenever it shows up. But E plus minus is such a beautiful, wonderful machine for measurements, but if you miss it, you miss it. You just miss that, by this width, you miss it. You don't see that. So that's now you can see that in general this formula is important, is useful. But most of the time you have a pair production, other things that this fraction is not as sharp as this, and that you are not dealing with this complication. So this is the first thing I want to show you. Let me quickly show you some numerics. This is the one. So I will not get into detail because of time. So as I mentioned to you, the production rate at E plus minus collider is not very high. So here you can see the profile. Here is the 90 GeV sharp peak. This is where the Z. This is the total cross section versus the machine designed center mass energy. I'm running center mass energy from 50 GeV to 90 GeV and the lab to 200 GeV, and the ILC will be around Higgs factory and 500 GeV International Linear Collider. And International Collider certainly has the capacity to move to 1 TeV, just making this longer. Of course, even further, but 1 TeV is currently designed. It's cost, right? It costs you money if you make it longer and longer. So that's the cross-section profile. You can see at the resonance, the cross-section rate is huge. So here on the other side of the vertical axis, I rescale that cross-section by multiplying that L, the luminosity, to give you the event rate. Okay, assuming that's just the constant, the delta function delivery. This is number of events per second for this the ILC future linear collider design luminosity, which is rather high, 10 to the 34-ish in that region. Okay, per centimeter square per that, which basically corresponds to, remember my scale 10 to the 33. This is 100 inverse femtobarn per year. So that delivers 100 inverse femtobarn per year luminosity, which basically means that if the cross section is as small as 100 femtobarn, and you deliver 1 event per year. But the cross section is pretty huge. 1 inverse femtobarn is here. And 10. This is 10. This is 10 inverse femtobarn here. That's in femtobarn. So therefore, you can see this is the number of events, and this is the cross section. And the general features are interesting. The Z peak, of course, the dominant. The next largest one, of course, this is the Barber scattering for electron. The reason electron Barber scattering is so big is a T channel. I told you this is a real singularity, Coulomb singularity. So it's electron in, electron out. Even there's no scattering, you still count the cross section. There's a zero. There's a 1 over T behavior, right? In the collinear region. Collinear region means the incoming outgoing is the same. There's no reaction because of long-term Coulomb force. Otherwise, this cross-section is not that very big. As I mentioned to you, that it typically, in the finite angle scattering, is typically always falls like this. Cross-section falls like 1 over s. General trend, unless you have a collinear radiation type of new contributions. That comes into like here. I will comment on these the next two. Okay, so that's the behavior. W pair production typically is the largest. So this is a W pair, and then once you cross the T-bar threshold, T-bar comes in. Once you cross the Higgs threshold, I mentioned to you Higgs mass plus Z mass. The Higgs will not be produced alone. It will have to be produced associated with another heavy particle to shake off a Higgs. Z Higgs associated production is the leading production channel, and that's where it comes in. So as interesting features, and I would be able to continue on quite a bit, but because of time, I leave that a few pages for you to read. So there are two important examples I want to show you, and to tell you. So the E+- collider can deliver very rich physics, very broad, very rich physics. I'll give you two examples, and I wrote more than two examples here, but you can read. The first one is the Higgs physics. Let's discuss the Higgs physics. This is major motivation for the linear collider, next international linear collider for the Higgs factory, as well as the so-called CEPC, right? Circular E+- as a Higgs factory. So that's the example I gave you. The general feature is a well-defined E+- kinematics that you can do. Suppose in the E+- collision, you produce an observable particle, something like a V, plus a bunch of other unobservable particles. Okay, so this is let's say like a Z, I mentioned there already, like mu plus mu minus and so on and so forth, it associated with something else. Then because of the energy momentum conservation, the initial state full momentum, full components, in a sense, will have to be balanced by the final state. Because of the well-defined kinematics, these four components are all well-defined, all measurable. Okay, unlike the proton luminosity is completely spread out. That luminosity function is called the parton luminosity function. It's completely spread out. It's even empirical. We can even not calculate from first principles. Okay. But this is the well-defined kinematics. In that case, you can move the observable particle around. So therefore, you can move the observable particle around there to have this E plus coming in, E minus coming in, and the final observable particle coming out that is equal to the unobservable generation. And let's square that. And this is the effective mass over there. And this is the effective mass for the missing whatever unobservable things. And you can determine what is missing. So that's this is called the recoil. Recoil from this guy, this is recoil mass against the observable. Okay. So this is the one. We call this if this is a single particle production, you have a peak. Mass peak. If there's not a single mass production, you still have the missing mass, bunch of particle missing mass there. If this is a single particle, then you hit the bump. So that is the E plus particle, E minus particle, and observable final state particles, whatever is observable, and that's it. And then even more, it is equal to plus minus square, center mass energy, and the observable square, the observable system mass. And because this is in the center mass frame, so the center mass energy here is twice the product. This is center mass energy. Once you know the observable mass, and this one is completely determined, model independent, whatever is produced. And this comes into this next example. We have this E plus minus 2 Z Higgs. That's the driving motivation for the Higgs factory for the next machine, because we have a very crude estimate. Even with the last week's update, the best measurement for the Higgs coupling branching fraction 10%-ish. Gamma may be slightly better. ZZ may be roughly there slightly better. Mostly it's around 20%, 10%-ish. Okay, so sorry you will not go with me to Heidelberg. Otherwise, I will give you the motivation, tell you why it's not even enough. Even not enough for the next level in TeV new physics, not even enough to understand. Therefore, we want to understand this well. Let's look at the clean channel. This clean channel, this guy will decay to something we can easily measure. And this is a V. We know that. So therefore, from this formula, and the Higgs mass bump will be modeled independently determined. Equal to central mass energy plus Z mass minus twice central mass energy and Z mass. Sorry, is that right? The energy. Mu plus mu minus energy. I think this is mu plus mu minus, yeah, this central mass energy. That's it. So the energy, this is energy. That's the energy product here. Okay, sorry. So you can see, you can, of course can measure this one, and we know it comes from the Z peak. Then the Higgs mass will be picked at the Higgs mass, and then this is model independent determination against any background. You just look up the events that happen to be in the Higgs mass. We know the Higgs mass to better than %. Now that's impressive measurement. Now the Higgs mass determination is better than 1% already. It's in fact 0.3%, 0.2, 0.3% already. So you can have that mass in that region. You pick up all these events. Then you count the number of events. You calculate everything. Calculate the branching fraction in a model independent way. You don't assume standard model here. You look up the events, count the number of events, and in this kinematic region we know, and you calculate all the properties. So this is called the recoil mass technique. This is the most important technique to have the best precision for the Higgs physics. So that's only available for this kind of a well-known, well-defined kinematic regime for the E plus minus collisions. So that's the first example I give you. There are many other good physics you can do. Let me give you one more. Let me give you one more example for this. One more example for the E plus minus collider. So once again, to utilize the well-defined, well-measured kinematics, that's a major advantage over the Hadron Collider, right? Let's think about the new particle production. Let's produce a pair of new particles. No preference, let's produce supersymmetry. Okay, so let's produce a pair of supersymmetry particles. Let's say you produce two scalar leptons, muons. Okay, just let's produce the muon. Let's say red-handed muons. Produce the new heavy particles. Once you cross the threshold, let's say each one of them is 200 GeV, then you build this 500 GeV machine, you produce two 200 GeV muons. This argument applies to any new pair production, okay, new physics production. So in that case, this one would decay to the observable particles. This is muon, then decay to muon, right? Decay to muon, standard model particle. But because of the supersymmetry quantum number, we call it R parity. And this supersymmetry particle will necessarily be associated with another supersymmetry particle. Typically, this is almost like a Z and a Z partner, or maybe a photon and photon partner. So in general, this is called a neutralino, neutral particle partner. It's a Z partner, photino Z partner mixed according to the interaction mixing. Okay, so that's one. In that case, this is the two-body kinematics we love. Remember, I emphasized the two-body kinematics is so well defined. So two-body kinematics tells you in the rest frame, in the muon rest frame, the muon energy is monochromatic, well defined. That is given by the center mass energy, of course, is the muon mass, and minus and plus muon mass, muon mass is 0, minus the neutrino mass, and the center mass energy again. That's the, remember there was a plus the muon mass, but that's what I gave you. But this is muon mass never be relevant. It's monochromatic. Then you see, boom, there's a muons with fixed energy. But in reality, not really. In reality, those guys will move around with the different directions. So that energy, this energy is smeared around, smeared out. But if you are able to reconstruct this center mass frame, this monochromatic, there's no background, you immediately know. You immediately translate into these two mass parameters. So that's inaccessible for Hadron Collider to any other places you don't have the well-defined kinematics. However, unfortunately, this muon in our lab frame will be smeared because of motion of these two guys. Those guys will produce with the beta and also at the different directions. It's not always at rest. So there's a spread out. But this spread out is also well defined. This spread out here is the 1 plus velocity, 1 minus velocity scaling. Gamma factor, So at the very end, you don't, instead of a monochromatic muon energy, you have a step function. This is the 1 minus gamma boost, and this is the 1 plus beta gamma boost. So you have a step function, but this end point is simply the function of this, the kinematics. So this is the example that you will be able to do this. Of course, you need to have other measurements like the total cross-section, scanning threshold to see this beta behavior, beta linear. This will be beta cubic because it's the scalar production. Scalar production has no angular momentum, and it's produced by spin 1, gamma z, whatever gamma z spin 1 to spin 0. Angular momentum, orbital angular momentum has to be 1. This orbital angular momentum has to be 1. It's L equal to 1. That's a p wave, and that p wave gives the beta cubic dependence. It's rather so. From that, you can, so there's a lot of measurements you can fix what this particle is. Once you know that, and this is an important aspect, you are able to determine the dark matter mass. This is basically the missing particle stable. Is the best candidate so far. WIMP, dark matter. Thanks God, Ruben is gone already. He won't challenge me. But this, I still think this is the best candidate for the WIMP dark matter. So then you can try to do that. So E plus minus will give you the best benefit for that. Because of time, I have a few more examples, including polarization and so on and so forth. I would skip. So let's get into the new aspects for the Hadron Colliders. Okay. So sorry for the little bit of rush, but you can tell that because of the clean environment, because of the well-defined kinematics, because of the possible polarization, and you have the potential for precision measurement for everything, including the Higgs, as well as the new particles. Once you are lucky to cross the threshold, okay, you have to produce a particle. Yes.
Can you please repeat what you're measuring?
We're measuring the muon energy. So so this one. So this is one. Suppose we produce a heavy pair, some new particle pair. I take this as a muon as an example, and then at the very end, this one will decay to a muon, this one will decay muon. You have the mu plus mu minus final state, but with a large missing energy. Yeah. So because missing energy is carried away by rather massive neutral particles to carry. This only participated the weak interaction, not the electromagnetic hadronic. It would not show up. So then suddenly the muon pair appeared in your final states. They don't fit your total center mass energy. So it's not really pair production. And then you have a missing particle. Then just measure the muon energy then. If you measure the muon energy, if this muon came out from a particle decay as a two-body decay, the muon energy will be a monochromatic, fixed value, given by those parameters here. You measure the energy spectrum, you could expect something that all the muons happen to be at the same energy beam. So that's the argument. However, because the muon would move either forward that way, sometimes the angular distribution this way, and then when you measure that, it's a boost against muon, boost enhance your muon, and so on and so forth, and that make this one a step function. Then you measure the muon, it's not a continuous spectrum, and this endpoint is determined by this kinematic factor. And the kinematic factor is a function for simply these two masses. And the muon mass can come from some place, some other measurement, but then you deduce the missing particle mass and the dark matter mass. So that's an illustration is, of course, a simplified version, but you can carry on more sophisticated channels and so on and so forth, but this illustrates the power that you can do. Okay, so let's move into the next topic to get into the more complicated situation. On the other hand, is our reality so far. Our reality is Hadron Collider at the LHC. Okay, the Hadron Collider at the LHC has major advantage for the for exploring particle physics as well, but has a certain disadvantage as well. Immediately, you can see it's not as clean as a two-body I can simply write. So that one is a partonic level E plus minus annihilation into some new pair production. But here, unfortunately, that's the strongly interacting the beams, and it's even not elementary particles in the initial states, the protons and antiprotons. So that's the protons. That's the situation. So therefore, we have to hope to separate out the fundamental process, and we call that a sub-process. The sub-process refers to the partonic level scattering, and the constituents we're dealing with to leading order will be quarks, gluons. So that's the initial beams instead of E plus minus. The initial beams really we are calculating in the perturbative treatment will be the quarks and gluons. That's what we calculate. So the gluons, quarks will initiate the reaction, then you calculate the dynamics, the matrix element squared, like that formula, and on. Of course, they are all strongly interacting, and quite often, dominantly by QCD effects, and the outgoing particles typically are colored, most likely colored, but of course we can focus on electroweak as well, but mostly colored, gluons, quarks, again, and those radiations, the collision radiations are just huge. So we have an initial state, something we call it ISR. Initial state radiation with these forward-going underlying events, so on and so forth. Initial state radiation going backwards, forward, but we even have a final state radiation because the final state FSR. Final state radiation means that even you produce high energy objects, quarks, gluons, and other things, they are so energetic, they are strongly interacting, their radiation is huge. Unlike the electromagnetic radiation. Electromagnetic radiation typically is order the fine structure coupling. And you read some, even you read some, it's not too big. But here it's huge, order 1. Radiation effects order 1. So very, very often. So that's the problem, okay. Quickly speaking, the total cross-section. So this is a cross-section plot similar to that one, but it's inconvenient. Look at the total cross-section. Total cross-section is hadronic. It's strongly interacting. The total cross-section is easily scaled, almost like geometrical cross-section, almost like a proton size, classical particles, Newton particles come in, and then the cross-section is a geometrical size. Of course, classical cross-section means that you shoot your darts, and there is a target. That's this board. And you don't have a reaction, you throw here. You don't have reaction, you throw here. You have reaction here. Therefore, it's classical area cross-section. The reason we translate that into cross-section is really this sense. You shoot darts to see whether their reaction takes place. Reaction takes place defined by this quantity, such as these areas give you in units. But that's huge. In fact, it's not quite proton size. In fact, it's really the interaction range. Really, it's a factor of something like a pion mass or some factor. But it's close. But so you can see it's huge. million bar. In fact, it's 100 million bars. In fact, that cross-section even goes almost like a constant, but it's in fact a logarithmic, a little bit logarithmic. And that part cannot be even understood. We don't understand how to calculate, but we have models or whatever to do that. So this is almost a geometrical cross-section, and that's huge. Most of these cross-section here, those events, we even don't care. That's a low-energy hadronic cross-section that happened how many years ago? In the 30s, more than that. In the 60s, in the 50s, 60s, 50s, we studied this a lot, right? We even don't care about this cross-section. The energy transfer, the Q square is irrelevant. Energy transfer is very, very low. Even this is so energetic, it's not in Lorentz event frame. You can imagine you sit on the proton with that, and the energy is zero. The energy is not Lorentz invariant quantity. It's the momentum transfer. That's why we sometimes call it transverse momentum. That is Lorentz invariant. Even you do the boost, transverse part is not changing. So that is a lot. But most of cross-section, very, very low momentum transfer. We really don't care. We want to get rid of them. We only care about the W production and the Higgs production that's 9 orders of magnitude below. The events you are interested in are 9 orders of magnitude below than the overall cross-section. You have to get rid of this. Not only you have to get rid of this, the fastest electronics so far would not be able to tape them. So far, so many events, how do you keep record of them? You cannot tape them. So that's called the selection. You have to decide what you want to select. And that is called a trigger. From our experimental terminology, called trigger. Now what do? You look for high transfer momentum. As I mentioned to you, only high transfer momentum is high momentum transfer. That's a high energy regime that we want to look into. Low energy regime, no matter how many events, no matter how energetic it is, not even Lorentz invariant quantity. It's not even the correct description. Your observation is different from mine. If you're sitting on top of a proton. Okay. You only want to look at the high momentum transfer one, and that's the selection, which is consistent with our detector design. Your detector design, you want to be away from the beam anyway. It's such huge radiation damage. You want to have your detector to be away from the beam. The beam is so strong and strongly interacting so many particles, it's immediately burned out your detector anyway. You want to make your detector slightly away from the beam, so that's you have the selection. So if from the TDR you can see that they have some selection. So this selection is called of course not only event selection but also called the trigger. I think this is the trigger list. Yeah, this is the trigger list. So you look for muons. I told you muons the best objects. They last most. So even for the muons, and you have to select the muons with the transfer momentum of few GeV. 6 GeVs is possible, but typically 15 to 20. Typically 15, 20 GeV. Those are the relevant muons. We keep them on tape. Anything lower than that, they are not even on tape. So you don't talk about those events at all. Sorry, we don't tape them. They are not even on tape. Okay, so that's the trigger selection. This is rapidity. I will come back next. I hope I have time to cover this. The rapidity, the pseudo rapidity has a 1-to-1 correspondence with our cosine theta. So the central rapidity is 90 degrees. Forward rapidity is a larger or smaller degrees. And the rapidity 2.4 is something like 10 degrees. Oh, here, 2.5. 2.5, 10 degrees. So 2.5 means the larger rapidity is more forward. Rapidity 0 is 90 degrees. Rapidity 5 is so far the detector can cover. It's absolutely impressive. They are able to cover rapidity, both Atlas CMS are able to cover rapidity 4.9, basically 5. It's 0.8 degrees, 1 degree. It's a tremendous achievement. They can, such a strong beam, detector can cover the collection of events, particles, at an angle with respect to beam around 1 degree. It's impressive. By the way, this was motivated by theorists, by phenomenology like us. At the time when this started designing 20 years ago at the SSC time, we were arguing that you want to do the gate boson scattering, you want to do the particle physics forward, the jets, and so on. So in the beginning, all you found the that's all bullshit. What they're talking about, we cannot do that. This is so important. Let's do it. That give you a little money, we can do it. So that's always the back and forth discussions. Theorists will have some reasons, which may or may not be right. So we do have reasons. And then those reasons will be passed on to our experimental colleagues to see whether feasible or not, and that's how 2 legs move forward theory and the experiment. That's how they manage that. So that's more or less the coverage for the detector. Okay. So the major advantages. So the major advantage for the Hadron Colliders, large cross section. A lot of events, even for the electrical processes, a lot of events, large number of events. This way surpass the Z factory for the Z already, but we will see the disadvantage. Large cross sections and very large, to some extent, is large center mass anyway. The LHC, so far, the reason is the protons are so much more massive than electrons. So it's so much easier to accelerate the very heavy object than the electrons. In the meantime, there's so much less synchrotron radiation. Remember, synchrotron radiation is energy, but divided by the mass, 4th power. So in that case, the synchrotron radiation is much less. The acceleration is more straightforward than the light particles for both reasons. So therefore, LHC energy now is running at a 13,000 GeV. In fact, designed with 14. Designed 14, which I think people still claim in the next round they will be able to reach, but it doesn't matter anymore. So in fact, the original starting point was 70 eV, half of that. And that was a Higgs discovery already. 780 TeV was sufficient to produce the Higgs by that time already. But now they are running for the moment, they're running very nicely, 13 TeV center mass energy. So that's a much larger, so therefore you have a much larger energy range to produce new particles like the heavy ones, the example they gave you, a few hundred eV. You have a much larger phase space to do that. Thirdly, higher luminosity available. For the same reason, protons are relatively easier to produce. Antiprotons, now people are able to produce large number as well from nuclear reactions and collect them. Technologically, they are able to cool them, to transfer, to make them beam. In fact, Nobel Prize winning. So W discovery had the 2 people to share Nobel Prize. One is Carl Rubia for the theory part, well, not theory part, for the physics part, and the other one as Van der Meer. He basically invented to make the antiproton beam effectively in the high luminosity. So that was a revolutionary. So for this one, so you have a high luminosity. Okay, so it's easily doable for 10 to the 34. That's what they are running, 10 to 34 per centimeter. Usually people don't use units, but that means per centimeter squared per second. So that's typically the case. So then you will be able to produce a large yield. Okay, 10 billion Ws and 100 million TD bar. In fact, this LHC is highly qualified as the first TD bar factory. Fermilab Tevatron discovered the top graph only. So in the original discovery is 10, 30 events, and now later it's a few hundred events. It's at 100,000 events level for Tevatron, only for the top graph discovery. Now it's produced the millions. Okay. So it's 100 million TD bars. In fact, so I have the one homework problem for you to calculate the Higgs rate. Did you get some number? How many Higgs do you produce a year? A million Higgs. A million you can produce many Higgs, but so many. But very difficult to dig out. Okay, so observation is very hard, but production, you produce a million per year for this. It's a lot. Okay. So that's every second or so you pop up a Higgs. Isn't that amazing? Of course, you don't easily identify them because of the detector aspect I gave you, and other things. Okay. Then another major advantage is exactly the one I said the advantage for E plus minus. E plus minus at the very top, I said they have a net charge 0 lepton number, 0 charge, and therefore you produce the new particles and so on. But this is different. You don't have you may have a non-zero charge particles to have a higher different quantum numbers. Okay, you may have the production from the constituents QQ bar that give you something similar to E plus minus. And you may have the gluons. And you may have different quantum numbers. You may have gluons and quark. It's not net charge. But you can produce the new particle that is a single, the two-third charged, new heavy particle. And then you have all different initial state quantum numbers, such as WW radiation. We call it vector boson fusion, right? VBF. And you have a ZZ initial state, photon, and so on and so forth. So you have all kinds of quantum numbers. You can produce the Q equal to 0, net 0, as the E plus minus only do. E plus minus only do the net charge 0 in the final state. You can produce the charge plus minus 1, okay? And you can produce the different angular momentum here, not the only partial wave 0, partial wave 1. You can produce this angular momentum 0, 1, and 2. You can produce the two angular momentum equal to 2. Gravitons. You can produce gravitons from gluon fusion, for example. Gluon is spin 1, gluon spin 1. They merge into graviton. Of course, it depends on interactions. If it's purely gravitational, and it's not quite the same. But large accurate dimensions, string theories, and so on and so forth, they do have examples like that. And the charge, you could plus minus 2 also if you have these like sign things. And isospin, the weak isospin. Isospin could be 0, and 1, and 2 also. Those are isospin triplet. So the advantage that here is that you have all set of possible quantum numbers, not a net 0 quantum number will produce. So that's another reason people usually argue the Hadron Collider may have a better chance for the so-called discovery. With a broader energy coverage, large enough event rates, all the possible available combinations of quantum numbers. So that's a major advantage. Okay. Can you see any disadvantage? You like them all? In fact, the major problem is this. The large cross-section in the previous slides becomes a very hostile environment. Most of the larger cross-sections come from the events you don't care, but you have to get rid of them. That's called background. Okay, so the background issue is a major issue. Major issue for not only for the experimental management, and also for our phenomenologists to see how to develop the schemes for the background suppression signal enhancement. And in order to do that, it's based on my argument for kinematics. So that's why I said, once again, I want to tell you the theme of the lectures, from kinematics to dynamics. You understand kinematics to a great level, and you dig out the underlying dynamics, how to emphasize your signal, how to suppress your background. So that's the major task for the LIC phenomenology. Cross-section, we discussed it already, and the trigger, we discussed it already. And there are let's go to one of these important difference here. I said the kinematics is much less favorable than the E plus minus, because E plus minus kinematics is so clean, well-defined, you know inertial state so well, and you can deduce what is happening in the final state. However, along this line, these things would not easily accessible. And this, you could do something similar to this because of the initial state uncertainty. This spectrum would be not as nice. It's so probably even no tail. So much worse. It's not non-existence, but much worse. Now let's look at why this is so. Okay. The reason is that even you have a proton beam A to have the momentum well defined up to something like a 10 to minus 3 level, beam energy spread. Okay. Along the z direction alone, no significant transverse xy components, and to have a head-on collision with proton B with energy opposite direction, and its mass is very important. It's pretty much the same. just opposite direction, so that they have a head-on collision. Okay. So the center mass frame let me see. The center mass frame is given by the energy. Let's see. Okay, so that's the beams. However, as I mentioned, at higher energies, thanks to QCD, thanks to the so-called asymptotic freedom, at higher energies, and the quarks and gluons sitting in the proton almost behave like free particles at a higher strong interactions. That comes from dynamics. And once again, Nobel Prize winning discovery, right? So at higher energies, the coupling constant becomes weaker and weaker, and all this perturbative treatment, similar to this kind of calculations, are valid. So thanks for that, and therefore we have partons. Oh, I gave this as a phenomenology example in the beginning, right? So in fact, we are talking about partons. The partons from the particle from the beam 1 carries only a fraction from 0 to 1 energy. Because of massless situation, you say this energy fraction x or momentum fraction x is approximately the same because the mass is gone. Mass is gone, magnitude, the momentum is same as energy. So that's why we could write this. You put x1 here, put x here too, because the mass is not relevant. So particle 2 is called a second parton, carries in general a different energy fraction. Different energy fraction. So the different energy fraction means that x1 plus x1 minus x2 is not 0. They are not head-on in general. Okay. So therefore, the center mass frame is not the lab frame. Fortunately, we don't have a transverse motion, but unfortunately, we have a longitudinal motion. So that's the parton center mass frame. The parton center mass frame is a center mass frame. We usually do our Feynman diagram calculations, our predictions, and so on, so forth. But it's related to the observation by the energy fraction, the carried by this one. So therefore, that's why in the other day I defined the transverse variable. Transverse variable in this region, that's okay. This is the same as the lab. There's no particular transverse motion. Longitudinal is not. There's a called a Lorentz boost, right? You know, the momentum and the energy, space and the time components mix, so that's a boost. And the XYZ will be rotation, SU3 rotation, as we learned from high school. But these are the boost, the time and the spatial, we only learn from Einstein or Lorentz. Okay, so that's there's a boost involved between these two systems. So there's a formula I don't discuss. The relative velocity will be once again momentum divided by energy. So momentum divided by energy, this is the velocity. The system, partonic system, is moving with the velocity, this velocity, with respect to your lab frame. Okay. Then velocity is one thing, but in the Lorentz transformation, there's another form to do the Lorentz transformation. One form is a gamma, beta. That's the high school textbook. We use beta and gamma. Another way to do that is slightly more elegant. Is use the rapidity. Right? So the rapidity is a different way to write the same thing in terms of the so this is called rapidity. It's a different parameterization to do the. So the rapidity is more like angles, the cos, the sinh type of rotation, things like that. And rapidity in general is from minus infinity to infinity. Okay. 0 is the central, as I said. 0 means that there's this beta is 0, cancel out. Beta equal to 0 means x1, x2 is the same. Therefore, that is a central region, no longitudinal motion. That is the region that the center mass frame of partons would coincide with the lab frame. So that's the rapidity. Otherwise, it's very, very, very fast, very, very rapid. So rapidity is 4. Rapidity refers something how fast it goes forward, how fast it goes backward. So that's the way they usually see. I will not give you the formula anymore because of time, but the only thing I want to tell you, this is a tremendous difference from this, the E plus minus reactions and the hadronic reactions there. Okay, so that's the major difference there. Then the other immediate consequence is, then how do we know the energy? You don't. You don't know the partonic energy, unfortunately. You know the proton-proton energy, but you don't know the partonic energy. But we could parameterize, see, we could guess. So how to think the partonic energy then? Now we have a U, D. That's what we learned from quark model, quark particle model, right? And Feynman, Gilman, and we were told. But in fact, this is only a model. It's not really the correct dynamics. Real correct dynamics is a QCD generates a strong interaction in the form of bond state due to gluons. A lot of gluons here. And that's real world. And these gluons will have vacuum polarization with the string quark, SS bar, and everything. In fact, in the real physical vacuum is not having nothing. Physical vacuum has everything at a quantum fluctuation level. So proton contains everything in terms of quantum fluctuation, depending on energies. At higher energies, and it will be more and more interactions with more and more gluons, and then more and more other particles coming up, including W and Z, including everything. So you can calculate the probability. So UD would contribute to the non-zero quantum numbers, like a charge, and also we call the valence quarks. Everything else, SS bar can be produced in pair, UU bar can be produced in pair, many more gluons can be produced in pair. Those other quarks we call it C quarks, ocean quarks from these. That's what we do. So therefore, we have to estimate how the energy distribution for those other quarks from these. So far, there's no first principle calculation. Okay, people are trying to make effort, in particular lattice-gated theory and so on and so forth. So far, we only parameterize from some general behavior and fit data. So that's called parton distribution functions. Parton distribution functions are parameterizations, trying to guess to our best level in comparison with the measurements. So that's what this is the industry. Very important industry in order to understand anything we want to do. It has been developed to a very sophisticated level. There are 3 or 4 major groups in the world. One in the US led by Michigan State University called CTEC, and a few. Durham is another huge group, and there's the next leading order QCD and so on and so forth. But I don't have time to describe them, but I want to give you some rough idea. Okay. The rough idea is that we should know some rough distribution for these. I guess that's almost the last topic we can do. Unfortunately, I did not get into my favorite part for the kinematics. I really have a favorite part for the kinematics, for the, again, similar to the E plus minus, how to deal with the S-channel resonance, how to deal with the missing particles, how much we can learn the missing particle kinematics, but that's all written in the notes. You go. Let's finally comment on this PDF and to tell you the pros and cons for this the proton collisions. Is that that's all? That's one related to this, but I have to skip. This is one. So in reality, we have a highly energetic protons, but provide the sub-processes, provide the partons. The partons, A and B, provide the fundamental underlying dynamics and the interactions, but with unknown energy distribution. But from general argument and also fitting, we can estimate the so-called the luminosity here. So the proton cross-section here, plus some particles, plus anything else, is similar convolution. It's your sub-process cross-section times the luminosity. We have gone through this on purpose. I went through this on purpose. In fact, in plus minus is so simple, I did not have to be that rigorous. But it's the same reason. In fact, when you calculate the cross-section or events, you need to calculate that sub-process cross-section and coupled with the energy distribution, the incoming energy distribution, the luminosity spectrum. This is the one we call the partonic luminosity distribution. So this is the parton luminosity distribution. Momentum distribution, let's say the momentum distribution for this probability of a parton, whatever parton, quarks and so, and momentum distribution of these. Have a guess what the U quark would look. Well, they contributed at the low energy, very, very low energy. They contributed major quantum numbers to that. 1/3 proton each. Okay, 1/3 momentum proton each. This is the momentum energy fraction. Here, this. It's about right. Distribution broad, something like 0.3 here, and U quark, D quark 0.2 here. So those are the U quark, the momentum distribution, like this. Okay, so the major contribution, the valence quarks would behave like this, parton distribution functions, roughly around this range. But at a higher, this is the low Q square, a few GeV. Few GeVs. At a higher Q squares, it shift up a little bit further, but this is one. However, you have a lot of gluons. A lot of gluons are very important to put all these things together and to generate at the smaller energy fraction. It costs gluon less and less. It still turn out the smaller energy fraction region is almost like a soft photons, right? Soft radiation. In the soft region, there are many more gluons. In that case, gluon distribution shows up. In fact, we even don't know where it ends because we don't know the underlying principle yet. People even argued maybe a kind of a saturation. Sure, maybe. But the valence quarks behave like this, contribute that. All the other C quarks trace the gluons because they are produced by the gluons. If something like this. So those are typical ones. That's best we can do. Then you have this distribution, you parameterize this, you fit data, you extract this as much as you can do, and you put this into this formula, calculate the cross-section. That's best you can do. Okay, so that's part of the distribution function. As I said, it's an industry, very important industry to make our search and discovery quantitative. That's very important. And because of this luminosity spectrum, because of the very broad spectrum, then you can see the complication that I discussed earlier for you. When this luminosity is sharper than your cross-section, when luminosity is broader than your cross-section, your luminosity is always broader than anything else. So your luminosity covers everything. Any resonance there, that's overlap, you pick it up. Your luminosity very broad, cover everything. That's why the good thing is that this luminosity is very broad for discovery. Bad thing is you don't know that very well, you hope it overlap with you that new physics maximally, which is the hope you can do. I think because of time, that's pretty much all I can share with. But I do encourage you to look at the other two examples that I did not give. One is S-channel resonance, how you view the S-channel resonance in the hadronic collision environments, and how you take care of that even with the missing particles like neutrino, and including the possible connection with missing dark matter particles, right? Get into that. And the other one is the T-channel, the features, and that is related to your homework for the photon collinear photon distribution functions. And in fact, at high energies, collinear behavior is very important. In fact, at high energies, collinear behavior is a dominant phenomenon all over places, both in terms of the initial state and final state I mentioned to you. It's dominant phenomenon in QCD. So that feature we should more or less know from kinematic viewpoint and uncover the underlying dynamics. So that part I don't have time to cover, but I wrote a few examples there, and you should take a look. Okay. So it's probably my fault. I was a little bit too slow in the beginning for the first two lectures, but I hope you understood what I want to say, and it built up the base to move on for the rest. I hope it was not a waste. Yeah. Okay, thank you very much, and that's it.
about proton-proton and lepton colliders, but what about electron-proton colliders? I mean, they in principle have only one part.
Yeah, exactly. Yeah, exactly. Very, very good. In fact, it's very, very good question, and that should be. If I had a few more lectures, I probably should fill in E gamma electron photon collision, which would here, and so that would be very interesting. And the next one, interesting one, would be EP, the one you mentioned. Kinematically is halfway in between. You are in better shape because one beam is well defined, and the only thing you don't know is this E with the transition between the electron and high energy collision with the proton. We call that a deepening, very similar to the deepening inelastic scattering. So proton in and a bunch of other particles coming out. And this momentum transfer here is much easier to calculate. So you basically know that in that case, in that sense, the particle distribution functions will be best defined. So most of the data to extract that one is typically is coming from fixed targets, this one, and another machine, EP machine, is called Hera at DAISY. So here you may know. It's of course the machine ceased to operate many years ago, but that one still provides the most clean, highest energy measurement for the proton structure. Now, of course, we have LHC energy you can extract, but it's not as clean as that. The good thing is that it's very, very clean, very pure test for the QCD, for proton structure, proton properties, and QCD aspects. That in that regard, best, no question. But in terms of discovery, it's somewhere in between, because you have a net charge lepton. Lepton number conservation is very rigorous. So far, unless a new particle carries a lepton number almost like the supersymmetry or lepton quark or something, you may not have the best chance for new discovery. It's somewhere between E plus or minus the Hadron Collider, because you have net quantum numbers, it has to be conserved. So you produce, which means electron something to produce a new particle. This new particle will have to carry this electron quantum number and the other quark quantum number. What is that? Lepton quark or supersymmetry particles. Only a few limited situations we can imagine. So in short, EP collider would be the best place to understand the QCD, understand the proton structure to the highest possible energy level. Okay. However, in terms of discovery, it depends on the model and depends on the underlying theory. We don't have a very broad coverage for a very broad variety of the theories. So that's the general remark for EP.
Yeah, so I don't see what the advantage is of having a PP collider over a PP bar collider, because it seems to me that all S-channel processes are suppressed because you have to go to a C-quark to get an S-channel. So why did they choose to build a PP collider over a PP bar collider like the Tempotron?
Protons are easier to produce than antiprotons.
Oh, that's the only reason.
I think to me, I think that's a major reason.
But if you could, then it would make sense.
In fact, the first proton antiproton collider was this SPP bar S. That's a very good point. Okay, that's a very important point. You should keep asking questions like this. So because this is a part of the conversation with our experimental colleagues, what may be best to dig out what the new physics we want. So the first one is called SPP bar S. The reason the P bar is P bar. P bar S is at the CERN, and that's I think the 630 from 540 GeV to 630 GeV. That's where the W and Z discovered. In that case, you have a proton and antiproton to collide, but antiproton has a valence quarks as U bar, D bar. That's the antiproton valence quarks because the antiparticle. Okay, so therefore, the leading production is Q bar, much more natural. So in that case, the Q bar annihilation give you almost like order magnitude larger cross section. That was designed to dig out the net quantum number to produce an WZ. That was a proposal to argue for that. to deliberately make antiprotons. It was a very technology didn't exist by that time. It was developed, and that's why Vladimir got the Nobel Prize. He developed the cooling system to be able to caustic cooling system to be able to reduce the transverse chaotic motion for the antiprotons when you produce them and make them all together march. So this march the same way. That's how they got the Nobel Prize. It's not easy. So antiprotons much harder to produce than protons. Protons, you and I made protons. Yeah, we have to create antiprotons. That's the reason. Now at very, very high energies, as I mentioned here, the quarks, antiquarks are almost similar, because the high energies, you have as many, unless you go to extremely heavy object production to reach this regime. Otherwise, it's no major difference anymore. For the Higgs production is from glue. It's not going to discriminate between proton and antiproton. Yes.
Right.
Yeah.
But the PDFs for C quarks are still much smaller than the PDFs for.
It depends on energy regime, as I said. Depends on energy. This is relatively low energy regime, and if you produce this, okay, that unfortunately I did not have the discussion. If you are probing a physics with a large X, the valence quarks are the dominant feature. Okay, if you produce the physics such as a Higgs, let's work this out. I hope you have a moment. Okay, so the effective central mass energy you can obtain is your proton central mass energy scaled down by these fractions.
Right.
So that's the one. Okay. So that is effective central mass energy. So therefore, if x1, x2 more or less same order of magnitude, x1, x2 would be whatever the new physics you are interested in. This is the physics you are interested in, and scaled by the machine. Okay. So that is the reason. Okay. Now, if you do the Higgs 100 GeV, and the proton central mass is a 10 TeV. Yeah. So this is 10 to the 4. Producing the Higgs, you are probing a proton fraction 0.1 and 0.01 squared to 10 to the 4. So you're using 0.01 structure function, square that, okay, x1, x2. This is dominant by gluons and valence quarks. Those guys not coming in. However, we are looking for Z prime. We are looking for 10 TeV Z prime. We are looking for 10 TeV Z prime. You substitute this by 10 TeV, too close to the borderline. That's 5 TeV Z prime. Okay, you are looking for a 5 TeV Z prime, and this is half. You're looking here. Very, very heavy object. For given limited energy, you're talking about large energy, proton energy, you're talking about a large energy fraction. That's valence quark contributes. That's general feature, yeah. Mm-hmm. Mm-hmm.